So, that was quiz 3. In a couple weeks we'll have quiz 4, and then right after that the final exam. So just a few more weeks left of this class. Today we're going to cover chapters 9 and 10, and just one little section from chapter 7. And then the following week we'll do chapter 11, and then we'll do chapter 12. And that's it. Okay, so this, or actually not next week. Next week is Thanksgiving, so we'll meet back in 2 weeks. That's December. And so normally the class is 12 weeks long, but your quarter is 11 weeks long. So in the past I would have 1 week before the final exam, which was just focused on review. So unfortunately we won't have that this quarter. I do have video recorded from previous quarters of the review session, but it won't be live. And I apologize for not getting last week's lecture up. I don't know what happened. I lost the memory card, which sounds so stupid, but that seems to be what happened. So I don't know. So I apologize for that. Okay. Are there any questions or issues before we move on? We're good? The material in this class is feeling okay? I feel like we're learning stuff. Did the lab go okay? This one is a little more straightforward, I think. Okay. Okay, so just to recap, we've learned the t-test and confidence intervals for the comparison of means from two groups. And from that we are able to make a comparison and say, you know, if I observe a sample with this mean and another sample with this mean, and if they're not exactly the same, can we then infer whether or not that difference is significant or not? Okay. Those tests are, or the t-test is known as what we call a parametric test, because the math behind it assumes that at some point things follow a normal distribution. Okay? And we see that when we have to check our conditions. Okay, there's conditions that we're supposed to check to make sure we can proceed with the test. Conditions like the sample was randomly selected and that the sample size is not too big and not too small. And those go into play so that we can assume that the underlying distribution is normal, and we do the test based on the t-distribution. Okay. We're in chapter 7. There's one section on 7:10, and we will learn something called the Wilcoxon Whitney with an H or no? It is Whitney test. Okay. Those are 3 last names of people who came up with this test. Okay. This is it falls under the family of non-parametric tests. Non-parametric tests don't put assumptions on the underlying data. No assumptions or minimal assumptions. In contrast to the t-test, confidence intervals where we assume y bar comes from a normal distribution. So the Wilcoxon-Mann-Whitney test, we're not putting any kind of assumptions on the underlying data. We're not going to assume that it comes from a normal distribution. And we still want to know if when we observe a sample, if that reflects a difference between the populations, okay? So we observe two samples. Reflects a difference in the population. Okay. But the difference here is not the difference in means, it's just, are the populations themselves different? So these are non-parametric tests, and so there's an entire branch of statistics dedicated to non-parametric tests. It's called non-parametric statistics, and you can spend your entire life, or at least an entire course, learning about non-parametric statistics. In our class, we are going to spend maybe about half an hour on it, and this will be your entire exposure to this branch of statistics, okay? But the rabbit hole goes much deeper, you can learn a lot more. But yeah, the basic premise is that we are not putting assumptions on the underlying data. So if you're not comfortable saying that the data, that y bar comes from a normal distribution, you might have to go with non-parametric tests, okay? But we saw from the central limit theorem that many times y bar will come from a normal distribution. So when can we not make this kind of assumption? Well, this is, we use our non-parametric tests when the conditions for the central limit theorem do not apply, okay? So, when should we use a non-parametric test? Okay. So, the answer is generally, when we cannot apply the central limit theorem and when are we unable to apply the central limit theorem? We're unable to apply the central limit theorem if our sample size is small, and it seems very clear that the underlying distribution is not normal. For example, outliers. Okay. So if you recall back to chapter 5 or chapter 6, I believe chapter 6, and we were talking about sampling distributions, we said that, or the central limit theorem, we said the central limit theorem holds if the underlying distribution, population, has a normal distribution. And if the parent population or the underlying distribution is normal, then any sample size is large enough. On the other hand, if the parent population is not normal, so we had those bimodal and those skewed ones, when you took small samples, it wasn't normally distributed, but when you took a large sample, it became normally distributed. So I don't know if you remember all of those R simulations that we did. That was to illustrate that when you took a large sample, even if the parent population was not normal, you still end up with a normal distribution. Okay? So if we're in the circumstance where it seems to be quite clear that the parent population is not normal, and our sample size is small, then the thing does not look like a normal distribution, and then you cannot use the central limit theorem. Okay? So this probably plays out, the most common scenario is you have a small sample, and within the sample there are outliers. And that would be a case where you would want to use a non-parametric test, because you would not want to assume that your sample mean comes from a normal distribution. So you would not want to make that assumption, so you would use a non-parametric test. Okay. But in general, a non-parametric test is less powerful than its parametric counterpart. Okay. Do you guys remember the meaning of power? I mentioned power, right? Type 1 error and type 2 error? Mm-hmm. Okay. And did I say the probability of a type 2 error is beta? Mm-hmm. And I said 1 minus beta is power? I did not say that. Okay. All right. So, on the side here, we'll talk about power. Power is equal to 1 minus beta. So beta is the probability of type 2 error. So anytime you do 1 minus something, that gives you the probability of what? The complement. Okay. So power describes how often we will not commit a type 2 error. So what would the complement of a type 2 error be? Type 2 error is we do not reject the null when the null is false. So that's an error, right? If the null is false, you're supposed to reject it, but we did not. So the complement of that would be the complement of a type 2 error is correctly rejecting the null when the null is false. Okay. So the power is equal to the probability of correctly rejecting the null when the null hypothesis is false. And that's a good thing. So if there is a fire, you want it to sound the alarm. If someone has the disease, you want it to show positive when they take the test. Okay? So it's the probability of correctly rejecting the null when the null is false. Or if somebody is guilty, you want them to be convicted in a court case. So power is the probability of making that correct decision. And in general, parametric tests are more powerful than non-parametric ones. Okay? Corresponding non-parametric test. And that's because the parametric test places assumptions on the data, and so if something deviates from those assumptions, we can say this is unusual. Meanwhile, non-parametric tests, we're not putting the same kinds of assumptions. So something has to be really unusual for us to say, oh, this is different. So anyway, let's talk about the Wilcoxon-Mann-Whitney test. And also, just a side note, our text highlights the Wilcoxon-Mann-Whitney test. And if you take another class in statistics, you might see something called the Wilcoxon rank sum test. This is the two tests are carried out in different methods, but essentially they're the same test. Okay, so they look different, but it turns out that the underlying math ends up being the same. Okay. All right. So anyway, we're learning the. I'm just going to abbreviate Wilcoxon-Mann-Whitney test, and. All right, and let's say here's our data, okay? So our data, we looked at two samples of data, two independent samples of data. So these are not paired. And I'm just going to use the example in the book. What they've done is they've gone to the forest and they've measured soil respiration data, okay? So I'm not entirely sure how soil respiration works, but you measure how much carbon dioxide is given off in the soil, okay? And these are the numbers they got, okay? And I'm going to already go ahead and put the numbers in order from least to greatest. That would be your first step. Just to save some time here, okay? So we have data from two sections. One, we have data from the growth section of the forest. So there, we went to the forest, and where there was lots of things growing, we measured soil respiration. And then we went to another section of the forest where there was kind of a gap in the growth, so not as many things were growing. And we measured soil respiration there. And so these are the numbers that came back. And so when we do the test, technically, or we do have hypotheses, but again, there's no parameters, there's no assumptions on the data, so we don't even have, we're not going to use any symbols for mu or symbols for whatever. We have to kind of write out the hypotheses, okay? So a null hypothesis would be the populations, the corresponding populations from which our samples are drawn we're just saying the distribution from which we're drawing our samples is the same for the gap section as it is for the growth section. Okay, so there's no symbols or anything like that. We're just saying that the respective populations have the same distribution. And then the alternative, okay, we can choose to have a directional or a non-directional alternative, okay? And so, I guess prior to looking at the data, you should decide whether it would be directional or non-directional, okay? So, if we go with non-directional, it would be something like the populations from which our samples are drawn. Populations have different distributions. If we decide to have a directional alternative, we might say the population from which the growth sample is drawn produces, or I should say tends to produce larger values than the population that corresponds to the gap data. So it's a lot more wordy in terms of writing out our hypotheses. So, but again, no parameters, no symbols for the mean or anything like that. We're just talking about the populations themselves. Are they the same or are they different? Or in the case of the directional one, we say the growth population seems to produce values that are larger than the gap population. Okay, is that all right? Okay, so let's say we decide to go with this alternative hypothesis. So we'll go with a directional test. Okay, can I erase this? No? All right, I'll let you guys finish writing. Okay, well, before I erase then, let's look at these numbers. So, looking at the numbers in the growth section, we can see why we might want to use the Wilcoxon-Mann-Whitney test. Because it seems that there are some large outliers that exist within a relatively small sample of data. Okay. So looking at this, we're getting numbers like 315, 190, versus all of these other small numbers. And so this would indicate that perhaps the underlying distribution for the growth data is not normally distributed. And so, and we have a small sample, so we would probably want to go with a non-parametric test. Okay, now I'm going to erase this. So if we're carrying out the non-parametric test, the first step, which I've already done, is put your data in order from least to greatest for both samples. And then you look at each number in a certain column, and you look at the other column and count how many numbers are smaller than this number, okay? So I'm going to look at this number 17, and how many numbers in the gap data are smaller than 17? Well, 6 is smaller, 13, 14, 15, and 16, these are all smaller. So I have 1, 2, 3, 4, 5 numbers that are smaller than 17. We go to the next number, 20. How many numbers are smaller? I have 1, 2, 3, 4, 5, 6 numbers that are smaller than 20 in the other column. Anytime you have ties, those are worth half, okay? So when I look at 22, I have 1, 2, 3, 4, 5, 6 numbers that are smaller, and I have a tie, so I write down 6.5, 6.5. Now if I had 22 listed twice in here, then each of those ties count as a half. So it would be 1, 2, 3, 4, 5, 6, and a half, and then if there were another 22, it would be another half, so I would write down a total of 7. I look at 64, and we can see that all of the numbers over here, and there's 8 of them, 1, 2, 3, 4, 5, 6, 7, 8. 8 numbers are smaller than 64, and that applies for the rest of our numbers as well. Okay, so looking at 170, 190, and 315, we have 8 numbers that are smaller. So in terms of, and these numbers contribute towards our, quote, test statistic. So in terms of the values, once you get past a certain point, the magnitude no longer matters. Okay, so we're not really worried that this one's 170 and this one's 315. It's just how many numbers in the other column are smaller. We do the same thing for the other side. So we go 6. None of the numbers over here are smaller. So I'm writing 0. So going on. At 18, I have one number that's smaller. At 22, I have 2 numbers that are smaller and the tie, so I write 2.5. And at 29, I have 3 numbers that are smaller. Okay. So step 2 would be for each number, each value, count how many observations in the other column are smaller. And then we add up these numbers. Add up those quote points. So if we add these up, I get 32 plus 17.5, 49.5. So the sum over here is 49.5, and the sum over here is 6.5. And so whichever number is larger, 49.5 versus 6.5, the larger one becomes our test statistic. Is equal to our larger sum. So over here we have 49.5. So we have a table in the back of our book for the Wilcoxon-Mann-Whitney test. And we are going to look up our test statistic in this table. So I think it's actually in your packet of reference tables that I've given you. So table 6. Go to table 6. Wilcoxon-Mann-Whitney test. Okay, so to use the table, you have to find n and n prime. Okay, so n and n prime corresponds to the sizes of your samples, where n is the sample with more items, and n prime is the sample with fewer items. Okay, so this is the sample with more, sample with fewer. And if there's a tie, then it doesn't matter. So in our case, we have 8 observations in the gap data. So our n is 8, and n prime is, we have 7 observations in the growth data. So we have 8 and 7 for n and n prime. Is that good? Okay, so I'm going to go where the column says n is 8 and n prime. I go to 7, and I look at the numbers, and the first number I see is 40 in bold print, and it corresponds to 0.189. And then it goes 43, 46, 48, 50, and 52. Is that okay? I'm just copying the bold numbers for n and n prime. 8 and 7. Okay, so we are looking for our test statistic 49.5. Okay, so our test statistic, whatever reason you use the letter U, 49.5. Okay, so if our test statistic turned out to be 40 exactly, the amount in our tail area would be